Hello everyone, this is Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In this video, we will see about the complementary energy. As we discussed in the last class, how to solve by using the complementary energy. Means once we will find the strain energy, okay, that already we proved in previous video that the strain energy is equals to the complementary energy, right? So now by finding a strain energy, that also we can just consider as a stored energy or strain energy, and with that we'll find the solution. So in this video we will see the principle of the stationary value of the total complementary energy and then application of the deflection problem is how complementary energy can be used for solving problems. So first is the principle of the stationary value of the total complementary energy. What is that principle? The principle of the stationary value of the total complementary energy may then be stated as, so what is that? So just see here, for an elastic body in equilibrium under the action of applied forces, the true internal forces, either force or a stress, that's force per unit area, so we can say either force or a stress, and reaction are those for which the total complementary energy has a stationary value. Meaning what? At equilibrium, for an elastic body at equilibrium, when force is applied, that time the total internal force and reaction for which the complementary energy has a fixed, that not varying values, means stationary values, that we can say that is the principle of this one. So in this what we will do. So now considering an elastic system, just we are deriving this how to find that. So considering an elastic system in equilibrium, supporting forces, just it's like P1, P2, P3, so on up to Pn, we are taking just number of forces. Okay, depending upon the numbers of forces given in the numerical, up to that we have to take. So first randomly we are taking from P1, P2, P3, so on up to Pn forces acting on the body when body is in equilibrium. And because of those P1, P2 forces, the real corresponding displacement is 1, 2, 3. That is, this one is actually delta 1, delta 2, delta 3, delta n, and so on. That change in length, that is small deflection, that displacement, right? So here delta is missing, so delta 1, delta 2, right? So P1, for P1, delta 1 is the displacement, for P2, delta 2 is the displacement. Now, if we impose virtual forces, now just we are assuming the virtual forces is delta P1, delta P2, delta P3, and so on, delta Pn on the system acting through the real displacement, then the total virtual work done by the system. So now here what we have taken, actual forces and then corresponding displacement. Now because of the virtual forces, real displacement, then what will be the work done? So then the total virtual work done will be what? Minus of, because this is the virtual one, so minus of for the whole volume y dp, right? That already we had seen the Cp formula, and this is the force into displacement. That also gives the energy, that for work done. So this is work done, and this is the complementary energy formula. So because of the virtual work. The first term in the above expression is the negative virtual work done by the particles in the elastic body. So this is the virtual work, and while the second term represents the virtual work of externally applied virtual forces. So what we applied the forces virtually here, delta P1, delta P2. So that's why here delta PR is there. Here we can change the value of R from 1 to n. So sigma or summation of R to 1 delta R PR, right? So as I mentioned here, this is delta 1, comma delta 2, comma so on, delta n. So here this delta 1 for corresponding P1, delta 1 will be there. Okay, so this we can write, I'm just writing this how we can write. So 1 to R is the is delta 1, delta P1 plus this delta 2, delta P2 plus so on, delta n, delta P. So instead of writing this is right in summarized way, this one. So this is because of the virtual load, and this is the virtual work done because of what? By the particle internally. Now from the principle of virtual work done, what? The sum of all the forces must be equals to 0 for equilibrium, right? So now this equals to 0. So minus integral of volume across the volume, we have to integrate across the volume. So that's why here it's volume y dp plus sigma r equals to 1 to n delta r dou pr equals to 0. So this previous equation should be equals to 0. The total virtual work or total work done equals to 0. Okay, that is from the principle of virtual work. Now compare this equation with the complementary C, that is complementary equation. We see that each term represents an increment in the complementary energy, right? So from once we will compare with the complementary energy that already we had seen in the previous video, we'll compare, means each term is getting increased. Okay, the first of the internal forces, the second of the external load. So here, what is that? Internal forces, and then here by this external loads. Now, so this equation we can write as what? Above equation may therefore be written as dou Ci plus C, that is equals to 0. Where dou Ci is what? Here Ci is for integral of the volume 0 to P y dp, just for this one, and C is what? Sigma of R equals to 1 to n dou R PR. So the see here if it's a positive, then this will be negative. Why? Because this is virtual work done user. So just for simplification, we are writing in this form. Just like for complex number, simply we are writing Ci theta. That is the meaning of cos I theta plus sin I theta. In the same way, if we will write, then Ci is this one, C is this one. Now, what we shall now call the quantity Ci plus C. So this quantity is overall is the total complementary energy of the system. So this is also the total complement sum of the virtual work done. Work done is stored in the form of energy. So thus instead of writing this much bigger, now we can say Ci plus Ce is the total energy stored in the system. Now application to deflection problem is how we can use this to find the deflection. Okay, so let us suppose that we require to find the deflection delta 2, right? Delta 1 also you can take that as one, just for normally the delta 2, then corresponding load will be P2. If you will take delta 1 deflection, then corresponding load P1 in the simple pin joint framework. So it's a simple pin joint framework is there. For that we have to find the delta 2 with the corresponding load P2. Okay, considering say of k members. So how many members are there? Total k members are there, means value will be from I equals to 1 to k, and supporting load P1, P2, P3, so on to Pn as shown in figure. So in next slide, that is here. Here is the figure 1, 2, that is 1, 2, 3, 4, so on, and number of forces is acting on this one, right? From the above equation, the total complementary energy of the framework is given by this, already we had seen, right? So C equals to I equals to 1 to K 0 to Fi, right? Lambda I dfi. So whatever is variable, according to that it's varying just here. Volume 0 to y dp or 0 to p dp. So here p is there. Now generalized way we are taking that fi, so dfi minus sigma r equals to 1 to n delta r pr, where pr is what? This p1, p2, p3, p so on up to pm. That already we had seen. Now here this, what is lambda I? So lambda I is the extension of the ith member, that, or you can say that already we found that we use this formula lambda equals to PL upon A. So delta L, that is strain, equals to PL upon A E. Okay, so by this same, this is here, that is the lambda. So lambda I we can write as PI LI by AI PI. If E same material is there, then EI will be constant, then no need to write EI. If all the members having the same cross section area, then simply AI becomes A, and we can take for all. Okay, Fi, Fi is the force in the ith member, and R the corresponding displacement of the rth load PR. So all related to, if suppose R1 we will take, then delta 1 P1, R equals to 2, then delta 2 P2. So what we are finding here for delta 2 means this will be delta 2 P2, because corresponding load we are taking as P2. Next is for the principle of a stationary value of the complementary energy that already we had seen. So this delta C, now just whatever is the value C is here, now differentiate this with respect to what? With respect to what we are finding? P2. So differentiate with respect to P2. So if we will differentiate with respect to P2, then what happened? dC by dP2 equals to, after differentiating, what happened? Differentiation and integration will get cancelled. So just see here, just only this sigma part will left. Okay, here. So this integration will cancel and this will be. So after this, sigma I equals to 1 to k lambda I, okay, then dfi minus. Now for this one, once you will differentiate with respect to PR, then simply delta R will left. Why? Because this PR will be like just 5x, differentiation of 5x is 5. So similarly here, differentiation of delta R PR with respect to PR is delta R. So now we got the differentiation here, so that we are finding for delta 2. So that's why with respect to delta P2, so here also delta P2 will be there, minus delta 2 equals to 0 for equilibrium. Right? Already we had seen that should be equated to 0 from the principle of energy conservation. Now this equation is seen to be identical to the principle of virtual forces, in which virtual forces dou F and dou P acts through real displacement lambda. So this we already had seen, that is similar to the complementary energy one. Right. So now this, where lambda is the extension of the, okay, from which what we will get? If this is 0, take this to this side. So now delta 2 becomes positive. So delta 2 equals to I equals to 1 to k. Okay, lambda I dou Fi by dou P2. So just take this as equation 1, because this equation is very important to find the deflection in the wind. Now we have to find this value, that lambda I value, to substitute in that equation, that is in this equation, to get the exact the delta 2 value or delta value. So here also discuss lambda is that for linear elasticity, lambda I equals to Fi Li by Ai Ei, where Li, Ai and Ei are the length, cross-sectional area and modulus of elasticity of the ith member. If first member we are taking, so suppose from here you are finding lambda 1, so I is 1, so this will be equals to F1 L1 by A1 E1, meaning what? Deflection or what? Strain, because in the first strain in the first member will be equals to forces acting on the first member, right, into length of the first member, okay, divided by cross-sectional area of the first member into Young's modulus of the first member. So when you are taking deflection of first member, then corresponding all the values of first member you have to take. If suppose similarly lambda 2 will be there, then this will be F2 L2 by A2 E2. Now if suppose that frame is given as same of the same material, means E1 will not change, because E1 depends on the property of the material, right? Same material means same E will be there. That time you can simply write directly as E. If in the question it's given that's having same cross section, then A1 A2 instead of A1 A2 you can use everywhere as A only. So if it's different, then A1 A2 A3, if it's same, then A. On the other hand, if the load displacement relationship is of a non-linear form, so this is for linear form, right? That already we had seen, F equals to that lambda Pi. So then in case of non-linear, then what happens? Then Fi will be equals to what? B lambda I power C. So if linear, then this C value will be equals to 1, in which B and C are known, right? then delta 2 equation comes. So now just put here in delta 2 formula. So Fi is what? From here, lambda we can replace in terms of Fi. So let's replace here. So what we have, lambda I equals to Fi Li by Ai Ei. Sorry, Ei. Now we are finding what value of lambda I from here, right? So first what we have to take, just take this one. So from here, Fi equals to B lambda I power C, right? Now take this to the side. So Fi by B equals to lambda I power C. So if this side we will take, then power will be 1 by C. So Fi by B, right, power 1 by C. This is equals to lambda I. Now what we have, delta equation here. So put that value here. So after putting what, we will get delta 2 equals to sigma I equals to 1 to K. Lambda value what we got here, Fi by B power 1 by C. So Fi by B power 1 by C into this dou Fi by dou P2. So now this will be the delta 2 values, right? So now let's see here, delta 2 equals to I. So what we got, delta 2 equals to Fi by B, that all we have seen in previous slide, Fi by B power 1 by C dou Fi by dou P2. So now what we have to find, this Fi by B power 1 by C means forces for each member, and then dou Fi with respect to dou P2. Okay. So now just see the question. Which type of question is possible from this one? So this is the structure, or you can see the frame, or reading with that frame. However, acting load P1, P2, P3. Here you can take that P4 also, P5, P7 up to Pn load is acting on this structure, which is simply supported here. Now, depending upon how many forces are given in the question, according to that you have to take. So let's see how we will solve this one. So we know that the support reaction do not appear in equation. So have you seen anywhere that support reaction is there? No, there is no support reaction, only the load acting or the virtual forces we are considering. So there is no support reaction. Okay. This convenient absence derives from the fact that the displacement delta 1, delta 2, delta 3, so on, delta n are the real displacement of the frame. Means here there is no reaction in that equation, means that reaction value is not required. How much reaction that simply supported or this will act on the surface, that is no need to consider. Means because if this is not, then whatever the actual force is acting, because of that only the displacement will be there, right? Means we will get the real displacement, okay, because we are not finding about the support. That means there is no, in the equation there is no term of reaction. So whatever displacement, that is just because of the acting load. Now the complementary energy of the reaction at A and the vertical reaction at B is therefore 0. So the complementary energy of the reaction at A and the vertical reaction at B. So just see here, at A, right, the reaction at A and the vertical reaction at B is therefore 0. So means it's not given in the question, means we can assume that is equals to 0 since both of their corresponding displacements are 0. Means here there is no displacement. No displacement means we can assume that complementary energy is 0. Now if we examine equation A, so just see here equation A, that's why I written this equation A different. So here delta 2. Now what we have to examine, let's say we know that lambda is the extension of the ith member of the framework due to the applied load P1, P2, P3, so on, Pn. Therefore, the loads Fi in the substitution of lambda I in equation A are those corresponding to the load P1, P2, P3, P and so on. Means now in this equation, right, what we will change that lambda I value in terms of Pi, already we had seen Pi Li by Ai Ei. So if we will change, the value should be same for the particular corresponding to that value. If suppose Li is there, that L1 is then lambda 1 is there, then P1, lambda 2, P2. Okay. The term dou Fi by dou P2 in equation A represent the rate of change of Fi. So how Fi is changing with respect to that acting force, that dou P2, okay, with P2, and is calculated by applying the load P2 to the unloaded frame. Means now these loads should not be there, only the P2 load should be there, because we are finding deflection because of P2. Means that time we have to assume only the P2 load is acting, remaining all other forces we will ignore. Okay, P2 to the unloaded frame and determining the corresponding member load in terms of P2. So now whatever the load is there, that we have to find in terms of P2. Why? Because we are assuming that only the P2 is acting and all other forces are not there or it's absent. So whatever we will get the load in terms of P2 only we have to consider. Now this is point to remember. That is the very important things. So for finding the solution, this point is very important. So just see one by one. This how to find that value. So this procedure indicates a method for obtaining the displacement of either a point on the frame in a direction not coincident with the line of action of a load. So see, this procedure indicates a method for obtaining the displacement of either a point on the frame in the direction not coincident with the line of action of force, or in fact a point such as C which carries no load at all. Meaning what? Here at C there is no load, right? Or here the C along this it's acting, right, along the line of forces. So it's not necessary that force must be along that line of the forces or line of the action only. Anywhere we can find. Here at C force is not there, then also deflection at C we can find by this method. Okay. We place at the point and in the required direction a fixus or dummy load, say PF. Means what? Now how we will do? Wherever is required, like at C we have to find, means we will put a fixus load or dummy load, just P fixus. Means fixus is there, so P fixus. Okay. Now after that, whatever the original load is there, that original load was what? With respect to P we are finding P2, so P2 we will remove. So the original load being removed. Okay. The load in the member due to PF are then calculated and dou F by dou PF, dou capital F by dou PF, the dou which is obtained for each member. Now what we have to do, once we will remove the dou P2, means now with respect to dou P2 we cannot find, we have to find with respect to what? The fixus force. So now force with respect to the fixus force, or you can say the rate of change of force with respect to the fixus force we have to find for each member. Okay, after finding dou PF value, substitute in equation 1 to get the required deflection. Now, in that also you have to take care of that what? It must be pointed out that it is not absolutely necessary to remove the actual load during the application of PF. So it's not necessary. You may remove or not depending upon the requirement. The force in each member would then be calculated in terms of the actual loading and PF. So now what is the actual loading and then in terms of PF. Now once we have that actual loading and in terms of PF, PF is what we consider that as fixus load. So then finding what we'll do, we will consider PF as 0. So Fi follows by substituting PF equals to 0, and hence dou Fi by dou PF is found by differentiation with respect to PF. So now whatever F is there, differentiate F, or you can say the Fi with respect to dou PF, find the value and substitute PF equals to 0 in the equation. How we will solve that we will see in the numerical. So first, next, obviously the two approaches yield the same expression for Fi and dou Fi by dou PF, although the latter is arithmetically clumsier. So finding this method is somewhat clumsier compared to this one, right? So for solving these things you have to remember. So just see once again, I am just telling. Okay, so once again, because these points are very important, if you will keep these points in mind, then only you can solve the numerical. So just I'm explaining once again, see properly. This procedure indicates a method for obtaining the displacement. By energy method, we can find the displacement of either a point on the frame in a direction not coincident with the line of action of a load, or in fact a point such as C which carries no load at all. Means by this method we can find the deflection of any point, either their load is acting or not. If there is no load acting on that particular point, then also we can find. If load is acting, then it's obvious we can find the displacement of that point, right? So that's why this method is easier, alright, and you can see that more applicable compared to the previous one. Now in that, how we will do? So we place at the point and in the required direction a fixed or dummy load. So at what point you have to find? According to that, the required direction, what we will do, we will put a fixed or dummy load. Just assume just give a name as PF. Now after putting the PF, what you have to do? Just remove all the original load acting. So whatever the earlier load is there, right, acting on that part, just remove that load. Then after removing it, what? The load in the member due to PF are then calculated. So now for each member, whatever the load is acting, just calculate with respect to finding, that means calculated, and dou F by dou PF obtained for each member. Once you have the PF, then find rate of change of capital F, that force, with respect to the fixed force, that is dou PF. Substitute in equation 1 to get the required deflection. Okay, next is must be pointed out that it is not absolutely necessary to remove the actual load during the application of PF. So just take care of this line, right? That it is not necessary to remove the actual load. Without removing actual load also we can find, right? The forces in each member would then be calculated in terms of actual loading and PF. So now after substituting PF, that assuming that fixed load or applying the fixed load PF, what we have to do? The force in each member. So find the force in each member, okay, with actual loading and PF. So what actual loading is there and PF is there, find the forces in each member. Once we have all the forces, then find Fi, that Fi follows by substituting Pf equals to 0. So now substitute Pf equals to 0. Why? Because already we assumed that as fixed load, virtual load, or you can say the dummy load, means we added, it's not given in the question. So once you added or we added, means that you have to remove that one. Otherwise, because of that load, again the deflection will get affected. So once, just for simplifying that one, we added that fixed load, and after that, while finding the proper or exact solution, just remove that load by putting that effect as 0, or that you can say the value of PF as 0, right? And then find what? Dou Fi by dou PF, okay, by differentiating with respect to PF, means differentiate Fi with respect to PF to find the rate of change of Fi with respect to dou PF. And after that, once you will see this one, or once you will differentiate, you can find that finding directly Fi is easier compared to the dou Fi, that is rate of change of Fi. So finding Fi expression is easier compared to the finding rate of change of Fi with respect to dou PF. That's why it's mentioned that the second one, that this one is the clumsier one. Okay, so this you can see, or this you can refer, okay, by the NPTEL courses, and the second one is from the THG Maxim Aircraft Structure for Engineering Student. That book is there, so you can refer for these two, okay, so that you will get the just for your reference. If suppose you have doubt, you can just put the comments and I will write you, or if you have any doubt, you can just contact me.
Like, share and subscribe. Hit the bell icon for more updates.